This is the second of my talks on matching and the final one on case control studies. So I've just been talking, in my previous talk I was talking about the advantages of matching, reasons to use matching. Now I want to say something about the disadvantages. And the first one is that matching can be very expensive. I think I've already mentioned this. So very expensive. And the more factors you have to match on, the more expensive it will be, because you have to screen a larger and larger number of potential controls before you can find somebody who satisfies all those matching criteria. So this alone means that you really shouldn't be carrying out matching unless it's really justified. As I mentioned before, it may be better just to kind of recruit a larger number of people, but you'll have to do the math to figure that one out. Another disadvantage of matching is that it may be necessary to exclude any case for whom no matching control can be obtained. And fortunately this is reasonably rare, but because usually we have more potential controls at least than available cases, but nonetheless it can occur. And in a situation like that, because you lose the case, it does reduce the study power, and also of course at the same time reduces the precision of your final results. Third reason, it's not possible to obtain valid odds ratios from the matched analysis for the matching factors, just because you've made them artificially similar to each other, the case and control groups. And often this doesn't matter because you've carried out, you have a good understanding of how the disease distributes, say in males versus females, or in one age group compared to another. So often this doesn't really matter, but I mention it anyway as something that should be taken into account. Then there's another issue which occasionally arises, and that is the problem of overmatching. And this involves unnecessary matching, and it can introduce bias, and it can decrease precision of your results, and it can cost you a lot of money unnecessarily. So we're going to talk about sorts of examples when you would have overmatching. So the first one is where the matching factor is a cause of the outcome, but it's not in any way correlated with the exposure of interest. An example of this might be, for example, if you were, say, interested in outcome being cataract of the eye, and if your exposure of interest was, say, sunlight exposure, and then if you were to match on, say, diabetes, because diabetes can cause cataract, and that would be probably unnecessary because it's unlikely that there would be any association between diabetes, as diabetes is the matching factor, and sunlight exposure is the exposure of interest. So it would be a complete waste of time and money. Doesn't introduce additional confounding, but you could have spent those additional resources on recruiting more cases or controls, say. Second, the second situation which would be very bad to match on was where the matching factor is not a cause of the outcome, but it was correlated with the exposure of interest. So not only is this a waste of time and money, but it introduces confounding when none was there. Like any matching factor will introduce confounding. It will make the case and control group more similar, and it will cause wider confidence intervals. So you would have to adjust on it anyway. But anyway, it's a very bad situation to match in. So here's an example of the sort of situation I was just talking about. So say that you were interested in the relationship between cigarette smoking and bladder cancer, but you chose to match on whether a person was a coffee drinker or not. So what would be the effect of that? Well, we've already discussed that there seems to be some relationship between coffee drinking and smoking, but it's not the coffee drinking which is the cause of bladder cancer. So if you were to match on coffee drinking, you would be making the case and control groups unnecessarily similar in terms of their smoking behavior. So this would potentially introduce some bias you would have to adjust for that, but in any case it would reduce the precision of the odds ratios. So that would be a bad situation in which to match. The third situation where you wouldn't want to match is when you have a situation with where you matched on an intermediate between the exposure of interest and the outcome. So a situation, going back to an example we've used before, if you were if you were interested in the relationship between alcohol and heart disease, and you were to match on HDL level, high density lipoprotein cholesterol level, which we know is an intermediate factor between alcohol and heart disease, then you would be basically seriously biasing the relationship, effectively largely removing the association between alcohol and heart disease. So definitely you would not want to do this, apart from being a very large waste of time and money. Now there are two sorts of matching, as we've already mentioned. There's frequency matching, and we normally use that just for the very common confounding variables such as age and gender. We know how the disease of interest distributes in those groups according to age or sex. So we would often use frequency matching for that purpose. Individual matching. Normally when we have a potential confounding factor which we want to match on, which has many different categories, and they would include neighbourhood or occupation, for example. And in the situation where we've talked about before, where you have a hospital case group and you use neighbourhood controls, you would match on neighbourhood in that situation. It is also a way of achieving a frequency match group. So just remind you of the situation with incidence density sampling, where we collect our cases and our controls more or less at the same time. Although we use individual matching here, this is really a way of achieving a frequency matched sample. And an example here, how we go about it, if we were looking at male breast cancer in the Bay Area, and we had these confounders to be matched on age, sex, ethnicity, city of residence, and that's quite a lot of confounders really to match on. But if we did, we would, and we had a case, it was a 55-year-old African-American male living in Richmond, we would then recruit another African-American male aged in that age band there, living in Richmond, and so on for all case subjects. So when we do our data analysis, we need to match on, we need to take into account the matching variables in the data analysis. And for frequency matched data, that's fairly straightforward. We just use the normal stratification method that we used, or unconditional logistic regression, if you were to go on, which you will learn if you were to go on in epidemiology. For the individually matched case, we use an individually matched analysis, individually matched stratified analysis, as I'll show you, or a conditional logistic regression analysis. So let's talk about the individually matched data, talk about how that differs from the analysis of data when we have a frequency match sample. So we have, this is a 2x2 table, and you recognize A, B, C, D, but the difference here is that the numbers in each of these cells actually represent pairs. And you see that the axes are labeled exposed case, unexposed case, exposed control, unexposed control. So we basically, with case control pairs, have four situations. So we have both the case and the control being exposed, or we have both the case and the control not being exposed. That's A and D, and we often refer to them as concordant pairs because they're basically the case and the control are just exactly the same. And then we have B and C, and we refer to these as discordant pairs. And so the situation for B is we have an exposed case and unexposed control. So they're different. And for C, we have an unexposed case and an exposed control. So again, the case and the control are different. And it's actually only the discordant pairs where there's a difference that contribute to the actual data analysis. So our odds ratio is not AD divided by BC, as it would be in a frequency matched sample. It's B divided by C. So B here, that discordant pair, divided by C, that discordant pair, the numbers of pairs. So if we put some actual figures in there, so if we have this number of case and control pairs, total number here, the 22 plus 167 do not contribute to the data analysis, neither that cell nor that cell. So that the odds ratio is determined by B, 127, divided by C, which is 76. Gives you an odds ratio of 1.67. But 48% don't contribute to the analysis. And we can say, just simply by the very fact of matching, this odds ratio here is actually effectively adjusted for the matching variables, whatever they may be, or maybe just one variable. So there is a correspondence between matched pairs and individual data. So if you think about, you remember A, B, C, small a, B, C, D. So you can calculate the 2x2 table that you are familiar with, most familiar with cases and controls, exposed and unexposed. So the small a will be A plus B, and so on. You can see how it works out, and so you can calculate that out, and you can work out the numbers in the 2x2 table that you're accustomed to, and you can calculate a separate odds ratio. So you can see it's a bit different to the odds ratio in this instance from using matched pairs, 1.67 versus 1.84. Now, so that really involves effectively breaking the match. And in some instances you can break the match in situations where you have sort of fairly common matching variables. Even if an individually matched method was used to select controls, as would be the case, for example, when we use the incidence density sampling to achieve a control group. So that's using an individually matched method to achieve a frequency matched method. So it may be perfectly all right if you're just using, say, age and gender, and you have sort of fairly broad categories of age, just to, as we say, break the match, as we did here, breaking the match, and then carry out the analysis. And very often you'll get a very similar result to what you would have done if you'd done the individually matched analysis. So I've tried this with various data sets, and usually they come out pretty similar. Using the matched analysis and then just the normal analysis. So that the illustration I showed you showed the very simplest example, which is just matched pairs, one case, one control. But it's often the case in practice that you might have two controls per case, in which case you have triplets, or maybe anything up to, say, 4 or 5, one case to 4 or 5 controls, and it can be more. So in those situations, the data analysis is hard to do on paper. It's much more complicated, and it usually relies on multivariate methods, particularly the method of conditional logistic regression. So as opposed to unconditional logistic regression, which is used for non-individually matched data. I just want to say a brief word about cohort studies. So matching in cohort studies, it does occasionally happen, but it's fairly rare. And there are a couple of reasons for that. And one of them is that usually cohorts are very much larger than case control studies, so you actually have to spend a lot more time and effort getting the matches. And the other reason is that if there's differential loss to follow-up, in other words, say an exposed person is lost but not the unexposed person, then basically you have to drop the the corresponding person. So basically you lose two people for every one, and this can substantially reduce the number of people in the study, and so it reduces study power. Now, you don't have to carry out any special matched analysis if you do matching in cohort studies, even though, as I mentioned, it's pretty rare. Just by matching, you're going to eliminate the confounding, but without the need to do a special matched analysis. So what's the reason for that? Why don't you need to have a matched analysis in a cohort study? The reason is that unlike a case control study, a cohort study it begins without any knowledge of disease status, and so that prevents the bias because you're only matching on the one thing, on the exposure. But in a case control study, the matching can be influenced both by exposure and disease, and that is what introduces the bias, and that's why you have to carry out an appropriate matched analysis to avoid that, but not so for cohort studies. So let me just sum up in regard to matching. It can be difficult and expensive and time consuming. That's the thing to sort of really keep in mind, and you can, in most studies, you can adjust for confounders in the data analysis without matching. Although there may be, as I've talked about, a number of situations where you might want to match, such as you've got a small case group, or your control group is likely to be very different to your case group, unless you match. The main benefit of matching, because we can adjust for confounding in other ways, is to increase the precision of the results, or to reduce the selection bias, such as in the using a hospital-based case group and using neighbourhood matching. The key thing to remember, though, is if you do match, limit it to strong confounding factors, and often that boils down to just age and gender. Often just age and gender. And finally, remember, you need to take the matching variables into account in your data analysis. So this is the last of my talks on case control studies, and I just wanted to conclude this particular talk by talking about the various steps that are involved in the design and setup of case control studies. So it's easy to get the impression by listening to talks on methods that it all happens very quickly, and but it's not the case. It can take years and years to go through the process of designing a case control study and getting through to the other end where you analyze the data and publish papers. So I just really wanted to very briefly go through the steps just to give you a sense of what it's all about, because there are a lot of conducting epidemiology studies is basic management and administration. So, but we often in the lectures we kind of emphasize the more interesting bits, such as the study design and the data analysis, and it's easy to forget that there are all these other bits that had to take place before you could get to the stage of data analysis or publishing papers. And this really applies to all epidemiology studies, but I'm particularly emphasizing it for case control studies, because the main reason for that is that they're such useful studies. And any of us, probably just about everybody who goes on epidemiology, at some point will do a case control study. So you should be aware of what's involved. So we often start with developing hypotheses, and then we think about our case identification and recruitment methods, and that may or may not be straightforward, but usually the control recruitment method is a much more problematic thing. We really need to have to think about that. We may even need to carry out some pilot studies to test whether or not the particular method works or not. And then we will have to develop some sort of very detailed proposal in order to obtain funding. And the proposal often has to be very detailed. It forces you to think out your study methods in advance, which is a good thing. But it takes time, can take months to develop a proposal. And then, of course, you go through the funding process, and if you seek funding, for example, from the National Institutes of Health, which is really the biggest biomedical funding body in the world, and they can be very generous with their grants when you can get them. But it's very competitive, of course. But typically you will have to submit your proposal twice. The second time, after taking into account reviewers' comments, and this process can take, right from the beginning to you getting funding, can take 18 months to 2 years. So it is very long and drawn out. So you should be in for the long haul. And then, of course, there's questionnaire design and pilot testing, and then you have to obtain the local IRB approval, but not just the local IRB approval, or IRB approval for all the sites where investigators are located and where the work is going to be carried out. And that can be demanding in itself, a lot of work in there. You have to prepare operating procedures for all the procedures that are going to take place in the study. Detailed operating procedures, and you have to train, you have to recruit, and you have to train staff in these procedures, including usually interviews for case control studies. You have to set up a database, and this is all before you've started collecting any information. The conduct of the study, that might take place over 2 or 3 years, and you've got to identify and contact your cases and recruit them, and then you've got to identify and recruit controls, appropriate controls, and then you've got to collect exposure data, including interviews, and enter all of this into a database, and carry out quality control of the data collection. So very important, quality control. So, and then there's a step of data entry. Often you will want to do double entry of data. So in a double entry, 2 separate people enter data. They enter just 2 separate databases, and then you use a software program, and SAS or Stata can do this, which compares the 2 data sets that have been entered and identifies all the discrepancies between them, and then a third person comes along and adjudicates between the 2 data entries, often by referring to a paper-based questionnaire, if you have a paper-based questionnaire. So, and then enters the correct value. So they can take quite a while. And then, of course, there's data cleanup and editing. So you have to kind of examine all the data, make sure it's been properly recorded, make sure all of the values that have been recorded are valid and what you want to see. And this can take quite a long time. Then it starts to get more exciting. You start to do the data analysis, which again can take quite a long time. You have to work with biostatisticians, and then interpreting the results, and then writing up papers and reports. So all of that can take quite a few years. So I say this really to my students, just so that if they're really wanting to go into epidemiology, they have a good feel for what it's all about. It can seem kind of glamorous at times, just when you're just looking at the results. It can seem kind of exciting, but in fact there's a lot of hard slog, and a lot of it involves meetings and administration and management and so on. All of these things are all very important. So and you can often employ good people who will do a lot of that for you, but in the early stages you will have to do a lot of it yourself. So that's the end of my talks on case control studies, and if you have any further questions on the study design or any of the aspects of it, feel free to get in touch with me. Happy to talk about it, or come to office hours.